Ravish. I'm Dean of the College of Arts and Sciences. Thank you for joining us tonight. I am pleased to welcome Dr. Neva Spake. She is Executive Vice Chancellor and Provost at Appalachian State University. Her career at App State spans nearly 30 years, beginning with her appointment to the faculty at App State's Department of History in 1996. She's held several leadership roles within the History Department, App State's College of Arts and Sciences, and the Division of Academic Affairs before being named permanently in her current position in May. Please join me in welcoming Neva Spake.
Thanks, Mike. Good evening, and thank you for attending this year's Morgan Science Lecture at Appalachian State University. This is the 29th lecture to be presented since the series began in 1989, established by a generous gift from G. William Morgan family. And thank you to the College of Arts and Sciences and the Department of Physics and Astronomy for organizing and hosting this year's event. The goal of these lectures is to stimulate scientific understanding and research by bringing innovative and prominent scholars to our campus. This is a collaborative effort with the Department of Biology, Chemistry and Fermentation Sciences, Geological and Environmental Sciences, and Physics and Astronomy, along with the College of Arts and Sciences, rotating leadership to ensure a broad spectrum of scientific topics are presented. This evening's lecture offers us a chance to take fresh thinking back to work and strengthen teaching across the university. I look forward to hearing from tonight's presenter. I'm pleased to introduce Dr. Sylvester James Gates Jr., a world-renowned theoretical physicist known for his work on supersymmetry, supergravity, and superstring theory. He is the John S. Toll Professor of Physics and holds the Clark Leadership Chair in Science at the University of Maryland. He is a distinguished university professor and serves as Professor of Physics in the Department of Physics, as well as a Professor of Public Policy in the School of Public Policy. Please join me in welcoming Dr. Gates.
Good evening. Is this thing on?
You have to use the hand mic for that.
Okay, no problem. Okay. This is for recording the talk.
AppTV.
Okay, very good. You've just watched a miracle, because you should never expect a theoretical physicist to do anything useful.
We have one more step.
Oh, see, I failed the test already.
We can turn it on.
Good evening. Yeah, I guess it's working now. Well, first of all, I got in on Sunday and have had an absolutely fabulous time here in Boone. In talking to this gentleman here, we made a deduction about me and Boone. Namely, the first time I came to Boone was about 40 years ago. But I was just on the highway and I didn't stop. So this is how close I've come. But like I said, it's just been a lovely, amazingly filled with hospitality visit. I've met some wonderful people here. And I hope I get back sometime. I'd like to bring the wife, actually, because you folks have some scenery here that is quite spectacular. So anyhow, let me get started with the talk tonight. Let's go here. Uh-oh. There we go. So I'm going to start in 1953 or 54 when I was living in St. John's, Newfoundland, Canada. My dad was in the U.S. Army, and most people don't know that after the Second World War, the United States had military bases all across Canada up until the middle 60s. So I was living there with Mom and Dad. We were living down here. You can see the main post headquarters. It was called Fort Pepperell. And in the upper picture, the regions back here in the upper part were the houses where the dependent families lived. So that's where I was in 54. And something happened while we were there. My mother took me to see a movie, a science fiction movie. Now, I think this is the first movie I ever saw in life, but it is certainly the first movie I remember seeing in my life. And it had the impact on me that when Father came home that evening, I told him I wanted to be a scientist when I grew up. So I was 4 years old when I started on this road to science. Now, the movie itself is terrible. But you can prove this because it's at YouTube. If you put that title in a search at YouTube, Space Ways, you can get it. Now, it's a movie, it's a love story, it's a murder mystery, and it's science fiction. And so you can see why it's kind of confusing, it doesn't know what it wants to be. But as that 4-year-old version of me, what I got out of it was there's this thing called science, and that science was a gateway to adventure and fun. What else does a 4-year-old boy want in life? So it was an easy choice to make. It was easy for me to say to Dad, I want to become a scientist. Now, I always wondered why my mother took me to this, because you see, my mother was a very artistic person. She did macrame, she did watercolor, she fired clay figurines, so, you know, very artistic in nature. And I always wondered why she took me to see this movie, because it wasn't something that she would be interested in. And eventually, I found out why, I believe. I know this is the movie because of the web. It took me 10 years to take the pictures from out of here, because I have pictures that I still carry in here of this movie, and I matched them against what's on the web, and that's how I finally found this movie. When I found it, I also found out that the star was this guy, Howard Duff. Well, Howard Duff, for a while, was married to my mother's favorite actress, Ida Lupino, and so I like to tell people, Ida Lupino is the person who really got me into science. So let's keep going. So, you know, science is an amazing thing because science I like to describe in several different ways, and not just science, but science and STEM, namely science, technology, engineering, mathematics. I like to call these humanity's survival instinct. Because you see, if we are challenged as a species by changing environments, it is going to be these three things that give us the tool to survive, and not just to survive, but to thrive in whatever comes after these challenges. So one of the things that we learned in science is that our universe has an age. It's about 14 billion years old. It started with something called the Big Bang, and this is a pictorial representation of the Big Bang. You can see there's a bright dot at the left side of this, and that represents the Big Bang, and our universe has been growing ever since. And so the thing that's interesting about this story is you should ask, how do scientists know these sorts of things? Why should you believe me as a scientist versus some guy who says, well, it all came from an elephant standing on a turtle's back? So what is it that science tells you to have this confidence? Well, the reason is because we have the receipts. We have the evidence. Now, many of you, maybe not so many now, but back a decade or two ago, there were these forensic science shows, and CSI was here, there, and the other, and the detectives would take a little piece of evidence, and they would string it together, and then they would figure out the crime. That's what we do. That's how we know this story. It's not something we made up. There are pieces of evidence that nature herself provides for us. And it is our task to figure out what the story is. And so we're doing forensic science. All of these stories are the forensic science of our universe. So, you know, you can start by asking simple questions like, what's the universe made of? And you know, when you first look at the universe, you might see leaves and trees, and then later you learn about molecules and atoms, and then someone comes along and tells you, well, atoms actually have protons and neutrons inside of them. And then about the time I was graduating from high school, we learned that protons and neutrons have smaller things inside of them. So it's a whole cascade of things that make our universe according to scientific observation and investigation. So there's something funny about this process. When you ask me about trees, I tell you I can see them, I can touch them. If you ask me about water, I say, well, I can feel it running on my hand. If you ask me about molecules, how do I know they're there? If you ask me about atoms, how do I know they're there? I can't see them, but I can build instruments that detect them. Now, I've never seen an electron either. But without knowing that the electron exists, you don't get high technology. You don't get TV, you don't get wireless, you don't get the web, you don't get social media. All of that stuff comes because someone figured out there's a piece of nature called the electron. Now, we know the person who did this, and it's not the person many of you may have heard, because a lot of people think it's J.J. Stoney, But in fact, that's not right. The first person to think of the idea of electron is a guy named I meant J.J. Thomson. But the first person to think of the idea was G.J. Stoney. So someone had to actually think of this thing before you can get electronics. That's how science works. You have an idea, you turn it into some sort of technological realization, and then that technological realization is the thing that the public and you, every one of us, that touches our lives and changes our lives in such a way that we can live more bountiful lives. That's how science works. So with me, I have followed, in my science, followed this chain down to smaller and smaller and smaller things and trying to understand what they are. Now, let me show you a picture. You see that bored kid with a lot of black hair in that picture? That would be me. That was a picture taken on the occasion of my getting my PhD. That's the person with the back is the president of MIT, Dr. Norbert. Oh my goodness, can't think of the guy's name. But I didn't want to be there. That's my face is so bored. But I had to be there for my standards because my dad was there. You see, I was the first in my family to go to college. My father never had the opportunity to go to college, even though desperately that was his desire. But he did want to make sure that all 4 of his children had the chance to go to college. And so I was the firstborn, his firstborn child. I'm named after him. And he came up for my graduation ceremony, so I was going to be there for him. Left MIT, went to Harvard for 3 years. That was a very interesting place. I started doing, when I was at MIT, I started doing some mathematics that nobody in the physics department nor the math department knew anything about. It was called supersymmetry, and this is the mathematics that lies at the heart of string theory. So I was actually studying string theory before string theory came into existence because I, as a graduate student, decided this is an interesting piece of math. Got to Harvard after MIT and wound up going to Caltech. Now, Caltech life started to get very interesting. There's this guy named Richard Feynman who is well known to people in the physics world. He was probably the smartest physicist after Einstein as we look back in time. Richard Feynman was utterly awesome. So I wound up working his research group. And this is from the period 80 to 82. There was another awesome person in the group, a guy named Murray Gell-Mann, and both Richard Feynman and Murray Gell-Mann were Nobel laureates in physics. And so I was a postdoc in their research group. Now I'll tell you a story about Richard shortly, because first I want to show you me. This is what I look like as a postdoc at Caltech. Kind of rebellious, independent-minded. Had already demonstrated that by picking out a piece of math that nobody at MIT knew anything about, and had a kind of confidence that the universe had an interesting story for me to tell. So I was pursuing that. Now, one day, right after I first got to Caltech, there was a gathering of the researchers in the group that Gell-Mann and Feynman led. And so I was sitting at a table, and about the distance that this young man is from me was sitting Richard Feynman. And I looked at, oh my God, I've been reading about this guy for decades. This is like super brilliant Einstein type guy. And he's sitting right there. He's a real person. I'm at the table with him. And he's talking to people around the table. I'm sitting there quietly because I'm thinking, if I open my mouth, you'll figure out I'm an idiot. And that won't feel very good. So I'm sitting there quietly listening to the conversation, smiling and nodding my head. And then finally he turns and looks at me and says, "Mr. Gates, that's your name, isn't it?" And I said, "Yes, Professor Feynman." And he said, "When I was your age, I wanted to wear my hair just like that." And suddenly in my mind, I had a picture of Richard Feynman with an afro. And because of that, I was never afraid to talk to this guy again. And here is Richard Feynman, one of the most brilliant physicists after Einstein to have made contributions. And in fact, in some sense, he's the father of quantum computing because he's the first person that's made statements about the possibility. Now, quantum is a word we talk about a lot. So I have a bunch of pictures that I use when I try to explain people what it is that I do. And I know many of you are very educated, so maybe some of this will be boring. But for a lot of the people in our general population, they don't know very much science. So when you talk or give a science talk, you have to go to where they are in order to present the material. And so what I'm showing you here is a diagram that is called a Feynman diagram, named after Richard Feynman. So let me tell you about the story that this diagram is showing. So the idea is that you have these two electrons that you see represented by the symbols E at the bottom of this image, and one electron moves along until it gets to this point, at which point it emits a photon, a particle of light. And this particle of light takes a message to the second electron on the other side of the screen, and the message is, I'm here. And I have the same charge that you have. And the way that electricity works, if you have like charged particles, they have to move apart. And so there's a message carrier that's actually causing that. The photon is that message carrier. That's the kind of physics that I worry about and think about. And Richard Feynman was the person who turned pages and pages of mathematics into this simple picture that I can tell anyone on the street. And that's part of the genius of Richard Feynman. Now, the picture that we just saw explains what you learned in high school. In high school, you were told like charges repel. They go like the product of the charges divided the square of the distance. That's how strong the force of repulsion is. But that picture, that story is true only if that first picture I showed you was true. It was all there was to physics. That first picture describes what we call classical physics. It's the physics that was known before quantum theory. It's the theory that comes out of the Coulomb's law about the time of Newton. That first picture describes mathematically what those folks were doing. However, we apparently live in a quantum universe. And a quantum universe says that that story of repulsion is not just that first picture. In fact, it says there are an infinite number of pictures that if you could measure the repulsion with infinite precision, you would require an infinite number of these pictures to explain the mathematics of how that measurement comes about. So this is another picture. This one is what we call a vertex correction. So let me go through the story. So here again, we see our same two electrons. This one moves along, but when it gets to this point, it emits a photon. That photon travels along and again, later gets reabsorbed by the same electron that emitted it. And we call this a vertex correction. If you could convert this picture to a piece of mathematics, it's different from, the repulsion that it gives you is different from what you learned in high school. And this happens to these pictures over and over again. I'll show you one more. This is what we call a vacuum correction. And in this picture, the story is the first electron moves along from here to here. It emits a photon. This photon travels through space and time, and then this photon disappears. When it disappears, it creates a particle and an antiparticle. And that's what you see in these two circles. I wish the animation was running because you would see something going like this. But these things have opposite charges. They get together, they recreate a second photon, and it's that second photon that tells the second electron you ought to be repelled. And again, the force law is not the one you learn in high school. And so quantum theory complicates what you think about and have been taught in high school as the laws of nature. Now, we don't do this just because it's fun, although maybe some of us do. We do this because this is how technology advances. When you learn more about how our universe works, you can build, ultimately, devices that take advantage of that advanced knowledge. And that advance then gives you more things that you can do in controlling nature. It's a cycle of things. Now, the interesting part of this process is that when you get these more things that you can do to control nature, you can make more careful measurements. And so this is the feedback loop between science, observation, mathematics, and technology. It's constantly going on, and that's why we have advances in our technology. For example, the web and the internet, most people think were invented by some great corporation. That turns out not to be true. It was scientists, people like me, who invented the web. And so with the web, we now see social media and all these other things, but that's not what the technology was invented for. It was invented for people like me to be able to talk about with our colleagues with tons of equations. That's what it was made for. But look at what it got us, right? So there it is, the movie's finally running. So that's the story, and like I said, there are infinite numbers of pictures, but I wanted to highlight you so you understand what it means when we physicists talk about a quantum correction to a classical law. Now, these things are measurable, these extra diagrams, because particles, like electrons, actually also have a magnetic property, And you can measure that magnetic property, and these extra diagrams contribute to the strength of that magnetic property. So if you measure the property, you can then ask yourself, does that agree with my mathematics? And if it does, then you are confident that the mathematics that you're talking about is not just some crazy fairy tale. That is an accurate description of our nature. And I have to tell you that this kind of experiment, which has been going on since the 50s, we have measured the strength of the magnetic moment of the electron, and for another particle called the muon, we've measured to better than 1 part in a billion, and it matches the mathematics to better than 1 part in a billion. There is nothing else that humans have ever done in science where you can make this statement of a measurement that agrees with the theoretical calculation to better than 1 part in a billion. So we're pretty sure we know what we're doing. So I have other heroes. And here, in addition to the photo of Richard Feynman, you have my hero Maximus. Uncle Albert, I call him, Albert Einstein. And so you can imagine a conversation between the two of them about gravity. Because after all, gravity, Einstein is the person who gave us the equivalent of Newton's law, gave us a mathematical equation that actually exceeds Newton's law in the description of gravity. And his equations are the things that first told us that black holes exist. Now, in the last decade or more, there's been experiments, the Laser Interferometry Gravitational Wave Observatory, LIGO, where we've been measuring these waves of gravity that were predicted by his equations. Now, you should wonder, how did that actually happen? Because you see, before Einstein wrote his equations, no one had ever thought about waves of gravity. So how do you discover something no one's ever thought about? Well, if you have a mathematical description of the idea, then you can use that mathematical description to say, if I did a certain observation, what should I see? And if you have enough computing power, because nowadays it actually turns out that the mathematics is so complex that sitting with paper and pencil is not going to give you the answers. You turn it over to the computers. But if you have that kind of technology, then what you can do is say, if this happens, I should see this pattern. And so the way that LIGO works, it's not like a safari. A lot of people think that scientific advances is you pay a lot of money. It's like going on a safari. You pay a lot of money, you go to someplace you've never been, you see something strange. Aha, there's a strange animal. That's not how advanced science works. What you do is you pay a lot of money because you got to pay for that technology. And believe me, we're talking about billions of dollars there. So you pay a lot of money, but then to find these new discoveries, you actually have to know what you're looking for. And that's where the science, the theory, and the computers come in, because they give you the templates of what to look for. And then you can say, aha, we have seen a gravity wave. And in 2014, that's what happened with the announcement of LIGO, that they had seen a gravity wave for the first time. So anyhow, back to our imaginary story here between Einstein and Feynman. So Einstein says, well, I gave you these equations, you got these gravity waves out of them, I'm pretty good. And Feynman says, but had a Professor Einstein. Does Mother Nature really say yes? Because remember, Feynman's the guy who does these diagrams. So Feynman's question would naturally be, where are my diagrams in your equation? Because if you don't have them there, you cannot talk about quantum corrections to gravity. So Einstein says, kind of, yeah, that may be true, but, I'm good. So let me talk about nature a little bit more. There are 4 fundamental forces in nature. There's the force of gravity. We all experiment, we all become physicists when we're around the age of 1.5 or 2 because we have to learn to walk. And so we have to figure out this thing called gravity, right? We all do this as normal human beings. But these other forces, well, maybe you stuck your finger in an electric plug around the house, so you learned about this thing called electricity. It was probably a very shocking experience. But there are other forces in nature. There are 2 other fundamental forces in nature. There's a strong nuclear force and there's a weak nuclear force. The strong nuclear force is that form of nuclear energy from which the sun derives its ability to deliver energy to us, light, heat, and etc. That strong nuclear force. There's another nuclear force called the weak nuclear force. And the simplest explanation I can give you about the weak nuclear force is if you're a science fiction fan, maybe you've seen movies from the 1950s where the radioactive monsters glowed. Well, the weak nuclear force is the source of that glow. So the weak nuclear force is a real thing, but in science fiction movies, that's how it's presented to the public. So there's 4 forces of nature. And so it turns out that Richard Feynman's picture-making way of correcting classical laws works for the strong nuclear force mostly. We have it excellently working for the weak nuclear force and for the electromagnetic force. So of these 4 fundamental forces, gravity is the only one that we don't know how to correct with respect to the laws of quantum gravity. So that's not a satisfactory situation. And so, once again, but Professor Feynman, do your pretty little pictures work for my theory? This is Einstein's question. This is the thing he's pressing us on. So it turns out the answer is no. We know how to take Feynman's mathematics and combine that with Einstein's mathematics in order to try to figure out how the little pictures work. But when we do that, the top diagram is the one that explains Newton's repulsion. Planetary bodies are attracted to each other proportional to the product of the masses divided by the square of the distance. And the rules for turning these pictures into equations on that first picture gives that same result. So classical gravitation without quantum, good. When you try to ask, well, can you draw pictures where gravity, by the way, the thing that communicates gravity from the Earth and Moon, we call these things gravitons. Just like photons communicate the electromagnetic repulsion, there are these things called gravitons that communicate the attraction between planets. And so this first picture, that wiggly G thing, that's the representative of a graviton, taking the message between Earth and Moon, you ought to be attracted. Now, we try to build quantum mechanics into this picture. And so, just like with electromagnetism, you say, well, you take your diagram that you had, you put a little loop in it. By the way, these things are called quantum loops. So you put a quantum loop into the mathematics, and you try to do the calculation, and you find out the answer is infinity. Yeah. Now, that's not a very convenient answer to have, because if the force of gravity was infinitely strong, the moon would be here, not 240,000 miles away. So you know something's wrong with this combination of mathematics, because it leads to nonsense answers. And so this is the basic problem of quantum gravity. And so, Professor Feynman. So I win this chess match because, because only the classical picture works. So you have to say, maybe the universe doesn't like quantum and gravity. Now that's kind of funny because we live in a universe that seems to like universal laws, right? It's not like the law of the sunrise only applies in the Western Hemisphere, right? The law of the sunrise applies everywhere we are on Earth. So we tend to think that the laws of physics are universal laws. For example, we think the law of gravity on Venus probably works like the law of gravity here on Earth or on Jupiter. So we look for these universal laws, and to say that 3 of the universe's laws are consistent with quantum mechanics and 1 is not, is inconsistent with the progress we as a species have made for about 600 years. So that's the problem of quantum gravity. Another person made a contribution to this. His name was Stephen Hawking. And back in the 80s, late 70s and 80s, he was again thinking about this problem. And he knew that Einstein's equations would never yield a solution to this problem. But you see, there was an alternative that was starting to be developed around that time. It's a theory called supergravity. Yes, this thing that I had been working on as a postdoc. And so Stephen organized a conference where he brought together mostly young people, but some old people, into a conference in 1980 at Cambridge University in England. It was called the Nuffield Conference, and this is the conference photo that you see here. I like to tell audiences like this that there was only one kid there with a really great tan. And that would be me. So Stephen, this is when I first met Stephen, and I met Stephen a number of times in my life after that. In fact, there's a movie called Hawking, Can You Hear Me?, which was released 3 years ago. It was basically the story of Stephen's life that the family wanted told. And if you actually watch this video, you'll find I'm actually in it. So me and this group of young people, by the way, this guy, Warren Siegel, another genius. I've only met 2 people in my life that I know are geniuses, and he's one of them. A genius is a person that they think thoughts that I can't figure out how they do it. But they do. I've seen it happen. So Warren and I actually, while we were at Harvard, were writing mathematical papers on this theory of supergravity, which is how we got brought to the attention of Stephen Hawking so that he invited us to this conference. Now, at this conference, a blackboard was created. And a few years ago, this is in 22, I guess, this blackboard that was created at this conference became a subject of an exhibition. And so here's the blackboard. That looks very scientific, doesn't it? Right? Not really, right? And in fact, I'm actually in this blackboard. So do you see me? Probably not, so let me help. So this blackboard was created by various ones of us at this conference. And by the way, I didn't actually draw that picture of me. In fact, you were not allowed to draw your own picture. You could only draw the picture of someone else. So that's why you see all these strange images there, because it's never the person themselves, it's someone else drawing them. But anyhow, that was the first time I met Stephen. We were worried about this theory of quantum gravity, and at the time, we didn't know what to do. But we told him everything that we knew about it. In 1984, so that picture was taken in 1980. In 1984, I resigned an assistant professorship in the mathematics department at MIT, and I assumed an associate professorship with tenure at the University of Maryland. I had a permanent job, right? I mean, that's the goal of being a faculty member. It's wonderful to be able to do something that starts off as a dream in your life when you're 4 years old, and at age 26 to be told, you can have this dream for the rest of your life. How many people get to have a life like that? So I realized how incredibly fortunate I was that I had been able to negotiate my life to that point. And this is a picture of me that was taken right after I first got to the University of Maryland. Still looking at this super stuff, which means I'm studying physics not at the level of blood cells, not at the level of DNA, not at the level of atoms, not at the level of the nucleus of the atom, but now where is it I think I'm studying physics? Well, I'm going to tell you another story. Suppose I had a yardstick, something like this long, from this hand to this hand, and I cut it into tentacle pieces and throw away 9. I would go from something about this long to about something like that. Okay? We're going to play this game again. Take that remaining piece of yardstick, cut it into tentacle pieces, throw away 9 and keep 1. You get something about as broad as my thumbnail. Everybody understand the game? Okay. How many times do I have to play this game to get to the size of an atom? Don't look at the screen. Anybody want to take a guess? Yes, sir. 413. No, sir. Someone else want to take a guess? Come on, don't be shy.
Already looked at the screen.
Already looked at the screen. The answer is 10. That's how many times you have to play this game to get from our world to the size of the atom. It's powers of 10. You do this process 10 times, you go from things that we see to the size of the atom. If you want to get to the size of the nucleus, as in nuclear energy, you play the game 15 times starting from our point of view. So that's how close the world of the atom and the world of the nucleus is to our everyday world, if you think about it, using this powers of 10 scale. Now, it turns out that we have reasons to believe that in this idea of trying to combine the quantum with general relativity as given to us by Einstein, we have suspicions that you have to start thinking about the universe at the scale of 10 to the minus 35 times. And then you have to play this game 35 times to get from our universe where we are down to where these things we call strings may exist. Now, string theory has an interesting history that is very complicated history, so I'm not going to take you into a lot of it, but let me just say that around 1980, a young physicist at Berkeley by the name of Dan Friedan showed us a way to get equations that work at that scale. And that's what you have to do to study string theory. So you don't watch the Big Bang Theory on TV. You learn the mathematics that Dan Friedan pointed us all to. Now, when you talk about string theory, it's got some beautiful pictures. You know, in my previous pictures, I showed you V's with wiggly lines and said that's how forces get around. Well, one of the beautiful things about strings is you don't have to have different things to produce the forces. So this is what's called a pants diagram for obvious reasons. Let me sew two of them together. And what you can see is the hoops on the outside look like the V's that we saw when we were just talking about particles. And in the middle, there's a piece of a tube. Well, that's where we saw a different kind of wiggly thing. And then on the outside again, you see that V shape. And this is giving you a message that the things that you thought from our perspective were different objects are in fact one object vibrating in different ways. That's one of the messages of string theory. It tells us that matter and energy are in fact the same thing mathematically. It tells us that space and time are in fact the same thing and that they are related to matter and energy. It's the only piece of science that has ever made this statement with a mathematical foundation. So anyhow, a lot of us got very excited in the middle 80s because of this. And I know a large part of the fraction of my community was working on mathematics trying to understand these ideas. By the early 2000s, these folks here and I had a conversation about string theory, and that video series that I did in '95, I guess it was. That's what happened after. And the answer is basically nothing. String theory has actually been at an impasse since about the late '90s, early 2000s. And I began to write scientific papers saying, you know, to the community that we need to think of some new ideas to get us out of this impasse. These are two of my papers. In fact, the one here, let me get this here. Actually, both of these papers was written while I was on sabbatical at Caltech. My thesis, this is a first page of a thesis that I did with my first female student, a young woman named Lubna Rana. And in my discussions with her, we began to uncover some new ideas that might get us out of the impasse that string theory has been stuck in. And the ideas are about pictures. Now, I showed you Feynman's pictures and how he uses them to explain quantum corrections. Well, I and Lubna began to see mathematical evidence that there were other kinds of pictures that might allow us to figure out how to put the quantum with gravity. Now, these pictures are like kind of weird, but it turns out to the right of this you see some mathematical equations. Mathematical equations contain data. To the left of this image you see some pictures. These pictures actually contain the exact same data. Now, how you figure out how to go from one to the other is not something I can explain to you, but it's something that I, along with a gentleman named Michael Fox, figured out in 2004. We figured out how to find the pictures that might allow us to do the combination. Now, these pictures we gave a name to. We called them Adinkras. And let me take a break here. I think if I can get just a moment. It turns out that these pictures part of the way you figure out is you ask the question about what's in our universe. And this is what I'm showing you here. In the lower left-hand quadrant are particles that we know about, including the electron. The electron is actually a member of a family of particles, the muon and the tau particle. And then there are neutrinos that we see represented here in the red sphere. This is what several hundred years of human exploration of our universe tells us is part of our universe. In the upper right-hand corner are particles, but these particles correspond to those wiggly lines that cause forces to move from one place to another. We call them gauge particles, or we can say they're particles of energy. The ones down here that include the electrons are particles of matter. And now I have a question for you. Does that chart look pretty or balanced? Probably no, right? And so when you start to see unbalanced things in nature, it gives you a suspicion that maybe you ought to balance it. Now, to balance it means to say that the universe has things you have not seen before. But you can't just say it in a random manner. You have to have some kind of idea of how to extend. And so this is what supersymmetry is. This is the mathematics I started studying in '75 as the only graduate student at MIT interested in this subject. That what would the universe look like if there's a balance in this chart? Now, these things we call Adinkras look like this. I'm going to show you some. These picture-making ways of taking equations and turning them into pictures, we extracted a set of rules for just building the pictures and forgetting about the equations. And when you do that, you can find things like this, like this, like this, like this, like this, and this, and this. And that's art. So we have made this strange transition from mathematics to art. Now, I did this with another gentleman, so let me make sure you folks understand that. I did this along with a gentleman by the name of Michael Fox. We're the first people to figure out how to take these equations that describe the balance and turn them into pieces of art. Now these pieces of art actually are, I don't know if there are any mathematicians in the audience, but there's a piece of mathematics called graph theory. And the images I am showing you belong in that piece of mathematics, of graph theory. And so the way that the discovery happened, you can see Michael there to the left, and you can see me to the right. In 2004, I was online reading, not social media, let me tell you that, but I was online reading about physics, and I saw a paper that Michael and a collaborator had posted. And the results in that paper looked strangely like the things that I had seen with my graduate student doing that PhD thesis. So I sent Michael a message saying, you know, are you aware that we've seen this similar stuff? And so Michael and I started an email conversation. Now, when this conversation started, I was in Georgia, but not the one you're thinking about. I was in Tbilisi, Georgia. And we had this conversation that went on for several weeks, and questions flowing back and forth, and Michael keeping a record of the questions. And at the end of several weeks, we had a scientific research paper. And the scientific research paper described how you can start with the equations and go to these pictures. That was the subject of the paper. And so by the end of this period, I was actually in West Africa, in the country of either Mali or Benin. I'm not really sure. And when we got these pictures, we said, these things we think are going to be important. We kind of did say, well, maybe this is a little bit like Richard Feynman's wiggly pictures. Maybe they will be, maybe not that important, but sort of. And so in physics, when you sort of get these kinds of discoveries, you get to name them. So Michael, who had traveled in Africa at least a decade before I ever stepped on the continent, suggested the name of Adinkra, this word that you see, A-D-I-K-N-R-A. Adinkra is a word drawn from the African tradition in West Africa of the Akan people, where they have these images that have hidden meaning. And that's exactly what we're doing here. We have these images that have hidden mathematical meaning. Now, there are two things I have to say at this point, because I want to make sure everybody understands. This doesn't mean that ancient Africans did supersymmetry, because there are people who will try to make you believe that. The other thing, however, is that we were like good colonialists and we just stole the word. So this is me with one of my students. In fact, this young man here is the kid who did the computer graphics that we were talking about earlier. His name is Ken Griggs. And I remind you folks, don't be afraid of mathematics, because you're not afraid of this. This is at least as complicated as a set of mathematical equations. This is Rachmaninoff's second, a piece I actually love and adore. I don't know how many of you are into that sort of thing, but I claim it is no more complicated than this. And this is what I study. So I'm kind of a composer of music, but the music is not the kind that you're used to. So these three sets of equations here are different. These are the three corresponding pictures. Now you might say those pictures look all the same, but there are subtle differences in them that correspond to the differences in those equations I showed you. So, and you can move these pictures around, it turns out. I'm doing calculus in these pictures. When I move these balls upward, I am doing derivatives. When I move the balls downward, I am doing integrals. Wouldn't it be great if your calculus course was take a bunch of beads, put them on a sheet of paper, and the teacher says, integrate this function. You just lift the beads up, and then differentiate this function. Just move the beads down. Wouldn't that be a great experience in calculus, right? A lot better than what normally happens in the calculus class. So, and we can move this in different shapes, and it turns out that these things, when you're manipulating these pictures, you're actually doing algebra and calculus in the equations. So it's not that the pictures only capture some information. They actually know about integrals and derivatives. And this is an object from a more complicated set of equations, and this is the one that has gotten me into more trouble with the public than any piece of science I've ever done. So you see that object that I started with. As I move balls left and right, I'm doing what's called matrix multiplication for those of you who are into that kind of thing. When I move, so I'm still just doing some matrix multiplication. When I move things vertically down, I'm integrals. As I said, that's when I'm doing calculus. And I'm going to do some more calculus here. So I'm now doing 4 integrals. Each of those balls is a function that you would write in a math equation. And now I'm going to do 3 more integrals. Now, at this point, you see that the left and right-hand sides look very similar to each other. And in fact, when we started out, it wasn't at all obvious that there were these copies of these things. And so the question is, are you looking at one object or are you looking at an object and its mirror reflection? That's the way to think about the question. And it turns out that you're looking at an object and its mirror reflection. I'll come back to that. The way we know this is very peculiar. In computer science and coding, there are things called error correcting codes. Without error correcting codes, you cannot have digital phones, you cannot have computers, because what error correcting codes do is account for something that's in our life. When I send you a message with a computer, what I'm doing is sending you strings of 1s and 0s. That's all computers know are 1s and 0s. And if I'm sending them on some kind of transmission, you know, in our world, accidents happen. So when I send you a set of 1s and 0s, in the transmission to you, some of those 1s might be replaced by 0s, and some of those 0s might be replaced by 1s, so that when my message gets to you, it's gibberish. And unless you can figure out how to fix that problem, then you can't have digital communication. Well, fortunately, back in the 40s, a guy named Shannon, Shannon was one. There were 2 computer scientists who figured out how to fix this problem. You have to introduce these things called error correction codes. And that folding that I just showed you involves error correction codes. This is crazy. This is the first time that a physical set of equations involve things that come from computer science. When I and my collaborators first wrote these papers, it took us 3 years to get a journal to accept our work, because I thought it was so crazy that it could not be right. It was a group of 3 physicists and 3 mathematicians, and we made this discovery. It eventually got published. But the public also found out about this because I made a joke. I wrote an article for an English journal called Physics World, in which I said, I'm a science fiction fan, and there's this movie called The Matrix. And in this movie, everything is in the Matrix. It's a simulation. We're a simulation. And I said something like, wouldn't that be great? Well, although I should have had one of those laugh emojis so I could put at the end of that sentence so everyone understood that this was a joke. But back when that was written, those emojis didn't exist. And so if you go on the web and type my name, Jim Gates, and the word physics, you will find tons of websites where people say Jim Gates has discovered we live in a simulation, that we are nothing but the matrix. Please know that's not what Jim Gates believes. Our discovery was highlighted in Physics World, and it was actually the cover story. I think this was 2010. And I've shown you lots of these Adinkras, so I'm going to skip ahead of them. And, oh, how to build them. This is childishly simple how you build these pictures. Start off with a square. Put open and closed dots at alternating vertices. Put different colors on every parallel line. Put an odd number of dashes on every square in the figure. That's how you get these equations. Those simple rules in the pictures generate the equations that come from physics. You can try a three-dimensional cube, do the same thing. Four-dimensional cube, because those of us who believe mathematics can do any number of dimensions we want, we can build physics equations out of these things with these as our starting points. So we've been through these pictures already. So let's get back. Oh yeah, some of our friends in London like to do things like this. This is Mark Richards, a friend of mine that is a physicist at Imperial College in London. So back to our Einstein stuff. So Uncle Albert still wants to know how to combine quantum theory with his theory. And I remind you that it's kind of a form of music. Here are his equations. His equations tell me things like gravity is actually not a force, it's the curvature of space-time. We have a cartoon here to illustrate that. Things like neutron stars can collide and coalesce in each other. As they do, they cause space and time to create ripples. These ripples are capable of traveling through space. And in the cartoon you're watching here, such ripples have been created in the first part, and they can come down, and we have built things like LIGO, which is down here on Earth, and we detect these ripples. Okay, so it turns out that these ripples are very interesting. Some of you may know about polarized light. Well, these ripples can have a different kind of polarization. I'm showing you some pictures of the ripples associated with the graviton. Feynman still wants us to get this right. Talks about the fact that the universe is allowed to have particles and antiparticles pop in and out of existence, and these affect our gravitational laws. And so in 95, two of my colleagues, Chris Hull and Paul Townsend, wrote a paper taking that first step of including supersymmetry with gravity in a way that might be quantum gravity. Since it's supersymmetry, it means my pictures are around the corner. Ed Witten also pushed this idea, and so in 95 there was born this thing called M theory, which is this combination. This is another one of my mentors, Abdus Salam, and his works actually got me studying things that look like this. This may not look as bad as that score, but it's awful. If you think of those dots as notes, this thing has 4 billion notes in it, the complete object. And so when Witten and my friends started talking about how to combine these things, they were talking about pieces of mathematics like this. 4 billion is a number so large that we could not figure out what was in the equations. You can actually write equations that are so complicated you can't figure out what's in them. And so this bothered me for a long time. I'm going to speed up a little bit here. And in 2020, working with two of my PhD students, Sesning Mak and Yangre Hu, we figured out how to take that thing with 4.9 billion notes and recast it in terms of one of our pictures. And because we could do that, we are the first people to be able to look inside of Ed's equations and see the graviton, the thing that causes the attraction between the Earth and the Moon. We know that it's there. We can also see some of the effects of the modifications of the laws of gravity that are in this object, because we can see inside of it, because we know these pictures are a tool for doing that. So that's the kind of stuff I do. Let me speed up and get to the end here. I tell young people, learn to code. Because that's the thing that gave me the vision, me and my students, the vision to be able to speak out the spins of 4.2 billion degrees of freedom in a quantum mechanical system. So learn to code if you're young. Even if you have white hair like me, if you can, try to learn. I've been using ChatGPT-5 for the last 3 weeks continuously. I'm learning some stuff. So Dirac once had this statement: living is worthwhile if one can contribute in some small way to the endless chain of progress. And that has been one of the things I have lived my life by. These little pieces of mathematics I'm showing you, let me give you a warning. Never trust a theorist. Never trust a theorist completely. Einstein had a comment about theories and theorists, and he said that when a new theory is constructed, the fate that it offers suffers is to be found incorrect shortly after birth. For those that do not meet this fate, nature only says maybe. And so we know that we've done the mathematics right, because we can do things no one else in the world can do in terms of looking at the physics of these objects that have been proposed for this combination of quantum and gravity. But is it the final answer? We don't know. At this point, I'd like to simply put up some acknowledgments, because the story I have told you, which spans several decades, has been empowered by a host of students, by my mathematician collaborators, by my physicist collaborators, and I'd like to make sure that people understand that theoretical physics is a very communal activity. People have this impression that geniuses go off in a corner and think this stuff up all by themselves. That's not how it actually works. You talk to your colleagues constantly. It's like swimming in a sea of information. So I want to acknowledge these people. And that's it, folks.
Imagine, but that was an hour, and I thought we were like halfway through. That was the most entertaining physics lecture I've ever sat through.
Well, thank you.
That was really good. We do have time for questions. I will walk around and try to give you the mic so that helps other folks hear it. So any questions that you'd like to ask? Sure, go for it. Yeah.
So, I mean, as you've said, every single time you think you discover something, you discover another smaller facet of it. Does it ever bother you personally? I mean, like God laughing at you over and over again, I guess?
Well, God may well be a jokester. That's one thing to understand. But no, you see, is this thing on?
I think it is.
Okay. But you see, that comment I made, that pointing to attention to that comment by Dirac, that's something I devoutly believe. It's not important whether I'm found right or wrong in my life. The important thing is that I have made a contribution that if it's right, it's going to be as important as Maxwell's equations, which led to Wi-Fi. That I care about.
Other questions? I have another mic I think that will work, but I'll walk out to you.
I was starting to think I had succeeded in putting everyone to sleep.
Hi.
Hello.
What do you think is the biggest flaw with the Adinkras theory?
I'm sorry, say again.
I said, what would you say is the biggest flaw, with the Adinkras theory?
What is the biggest flaw? The biggest flaw is that I have yet to be able to find the equation I am looking for. Adinkras are a tool. They're not the end result. And the equation that I am looking for, I showed you Einstein's equations. I want the Adinkras extension of that equation. That's what I'm looking for.
that the many worlds interpretation of quantum mechanics is the best present explanation we have for quantum mechanics, basically?
No.
Why?
Thank you. Because, to my knowledge, no one has ever found a prediction in the many worlds proposition that is measurable. If you can't do that, it's not science.
Hello, Jim. It's me again with another nerd question.
Okay.
You said that you think that, you said that gravity is not a force, but it's a bending of space-time, whereas the other three fundamental quote-unquote forces are forces. So why?
Why? You want to know why?
My question specifically is, why do you think that gravity needs to be combined with quantum mechanics? Like, what are the specific reasons that show us that that's necessary?
I can give you two reasons. They're called Stephen Hawking. You see, Hawking's work in the early 80s is a statement that black holes are not completely black, that in fact black holes emit thermal radiation. It's called Bekenstein-Hawking radiation. And unless you have and when Hawking made this discovery, it is only true if quantum mechanics is there. And so that's why we worry about such things. And by the way, within the last 2 weeks or so, there has been an announcement from LIGO where they have been watching the coalescence of either black holes or neutron stars, black holes specifically. And the announcement is that the law of radiation that Hawking proposed in his 1980s work has now been verified by this LIGO observation. So that's why people need to worry about these things.
Thank you for your talk, by the way. My question is, in the next few decades, how do you visualize these progressions being integrated into society?
I am 74 years old. Therefore, I don't envision how things are going to be integrated into society because I don't know. I can only tell you fairy tales that happen to be true. Let me get this right. In 1876, James Clerk Maxwell wrote 4 equations which describe everything that had been discovered up to that point in time about how electricity and magnetism works. When he wrote his equations, he took basically equations that people had written before. Just like tonight I was talking about what I want to do is take Einstein's equations and add something to it. He took equations that people had written before him and he added one term. The reason he added the term is because without this term, the equations are actually mathematically inconsistent. But when you add this term to his equations, what you find is that electricity can flow outside of wires. We have a name for that. We call it radio and Wi-Fi. So 1867, when does radio come into existence? Early 1900s, so that's 40 years. So the kind of science that I do work on and the stuff I hope I'm making a contribution, these are things that are basically century-long bets. And I could easily lose, but someone's got to do it.
Do you feel like the visual representation of the Adinkras, like the very beautiful way they look, connects you back to the arts of your mom that you grew up around?
No one's ever asked me that question before. In a way, maybe. I've always been a very visual person. When I was younger, I drew pictures of airplanes and boats and ships, not just of the exteriors, but what were called cutaway views, where you see the cruise compartments and those sorts of things. So I have always been a visual person. When I was in my first year of college at MIT, the first class I took was in physics was about Newton's second law and its implications. I had a very difficult time passing that class. The second class I took was on electricity and magnetism, where those equations that I just spoke to this young lady about were shown to me for the first time. But there were pictures associated with those equations. And because of that, I found it remarkably easier to understand the complicated calculus of physics. So this has always been part of one of the apps that runs in my mind, that math and images are inextricably connected. And I have used them all of my life. In that first example, when I became aware of it, to get a really good grade, right? Because I could do that connection. But since then, I have used this habit repeatedly to do things other people don't see.
Do you think the math exists to explain supergravity as it is now?
Not completely. We understand a lot about supergravity, but not to the point where I can make it add to Einstein's equation. That's my goal.
So you seem like a lover of sci-fi movies since a young age. So do you think that there are any currently that you think are a good, like aren't absolute bullcrap? Don't mind my language.
Well, in other versions of talks that I've given on campus, people will confirm your supposition about my love of science fiction. Because as I said in an earlier talk, that when I was a teenager, the reading of Marvel comic books was one of the things that have made me successful as a scientist. I gave up reading comic books when I went away to college. So I gave up reading science fiction when I got my first faculty position. So it is certainly true that over the course of the last decade and a half or so, as Marvel has moved to the movie screen, I have enjoyed some of those maybe first 6 or 7 productions. People in the know are laughing because they know why. That's a true statement. And so, since I don't read science fiction anymore, and since I don't read comic books, and since I have been extraordinarily disappointed in the evolution of the Marvel story, I don't know how to give you an encouraging answer to your question.
As I was looking at your the art that was generated by the Adinkra, it was reminding me of fractal geometry. Is there any correlation between the equations there?
That's a great question. This is something those of us who have studied this for the last 2 decades or so have asked repeatedly. There's no mathematical evidence of fractals in these constructions.
In the visual representations that you
I'm sorry, speak up a little bit.
Oh, sorry. In the visual representations, right, is there like an analog for entanglement that you found?
So far, no.
Really? That's crazy.
Well, I have colleagues who are actually looking to see whether those visual representations allow quantum error correction. Remember, I kept saying error correction, but I'm talking classical error correction. I have colleagues who have been looking for the signs of quantum error corrections. So far, the answer is no.
I don't know, maybe I missed it, but why is your presentation called Adinkra-2-Adynkras with a Y?
Well, at the end, I stopped the talk precisely at 8 because I was told to do so. But it turns out that what I've told you is roughly 3/4 of the story, but not the whole story. And the whole story involves an entirely new set of graphs that are not built from these hypercubes, but have a different origin and are related to the hypercubes. And if I had been faster in getting through the prior stuff, I would have shown that in more detail. Because there are a set of graphs that we have found that are even more powerful. And this recent discovery is 5 years old. So. Yes, I don't know if you're a mathematician, but there was a great Russian mathematician named, last name Dinkin. I think the first name was Yevgeny. And it turns out that this second generation of objects that we have constructed, we've taken advantage of some of the mathematics created by this Russian mathematician, and his name is spelled Dynkin, D-Y-N-K-I-N. Are we done?
One more. Okay, I'll go for two more here.
Thank you. This has been really cool, and I think you've done a great job explaining really complicated things in a way that are at least vaguely understandable to the lay public. But it makes me wonder about advancing these kind of ideas, and maybe related to that question about do the mathematics exist to do this kind of thing. Are things becoming complicated enough that the training of folks coming into the field, like how can you understand these things well enough to continue making advances? Is there a limit to progress, or are there structural problems where folks training, you need to be almost retired to be able to make an actual advance to the field? Like, do you have any thoughts on that kind of thing?
So let me presage my answer by telling you that I often describe myself as a codger curmudgeon. And so a codger curmudgeon is about to give you an answer. I worry about some of these things also because the mathematics gets so complicated. And in particular, in our society, I worry a lot because I was born in 1950, and the fact that I'm a scientist is kind of perhaps expected because when I was growing up, science was not being attacked, and in fact, the general public supported science and understood that although science is not perfect, it was a way to improve the quality of our life. The Salk vaccine cured polio in this country. The nuclear bomb, the atomic bomb, a terrible weapon of destruction, ended a war. And had it not been dropped, probably millions of more people would have died. So when I was born, and in the years that I was before my adulthood, this appreciation of the power of science to do good in the world was generally accepted by our society. And that encouraged many people to study it. We now live in a time where this is simply not true. And so I worry that the currents that I see in my society mean that the number of young people who want to pursue this stuff, because I'm not going to become a millionaire doing this, right? I do this because it's a deep passion of mine. But money matters in people's lives. And as our country disinvests in science, which is what it is doing right now, it will close off pathways for people who even want to do this because they won't be able financially to find a way forward. So this is my biggest concern about what's going to happen to science in this country. As a society, it looks like we're pulling away from it. I should tell you, this is something I've been worried about for 20 years. I gave a speech in 2005 before the annual Association for the American Association for the Advancement of Science. And in that speech, I pointed out that there were signs that this is the direction our country would take. In the intervening 20 years, these signs have only gotten more dire.
I guess kind of like bouncing off of that, as someone who was like first generation in your family to also go to college, what would you say to someone who wants to do science for the rest of their life just because they love it?
That's why I did it. And it is one of the most satisfying things that one can have, in my opinion, is to live one's life doing what one loves. Society may not allow that. I understand how fortunate I have been that I lived at a time and in a country that this dream could be realized without me taking a vow of poverty. It's not clear that this is going to continue. This is not to be a downer, it's just to make a statement about what I believe.
Okay, you can correct me if I'm wrong, but you did serve on Obama's advisors board. Was there anything you pushed them to research more, or like was there a huge concentration you had when you served on that board?
Thank you for that question. I am a professor of public policy because of that, and so I still think about and work in public policy domain. So so the group, first of all, for the larger audience, every president up until the current one has had a group of advisors, and the group is called the Presidential Council of Advisors on Science and Technology. So I was a member, there are about 30 of us, and you asked personally what I did, so the things that were most directly in my control were the 4 reports that administration accepted on STEM education. The first of these reports is called To Prepare and Inspire. It is a set of, I see some people shaking their head, maybe they're familiar. It was a report on what might be done to make it possible for American children in grades K through 12 to be better prepared to engage in STEM studies. The second report, again, the way that the council worked is individual members of the account were given responsibilities to do these reports. And so the second report on education, STEM education, is called Engage to Excel. It concentrates on what might be done in the first 2 years of college in order to create wider and broader pathways for young people to get into STEM-related issues. Now, you need to understand that it was never the purpose of these documents to necessarily create more scientists, but what we did wish to do is to create a more scientifically literate population, because that's where you get the support from science from such a population. Now, I have to tell you that on this visit here at Appalachian State, I have seen remnants of that work. In our reports, we were talking about things that could be done to get young people who say they have an interest in STEM fields to also become teachers. There are people on this campus that actually took advantage of those programs when they were created. This was, to me, one of the greatest joys of this visit. Some of the techniques and approaches that we talked about in those reports about using things like we used to call them clickers. Again, in talking to faculty members here, I heard faculty say, yeah, we're using clickers. That came from those reports. So I have had a chance to impact my country at a level that is far beyond anything I ever imagined, and I'm very grateful for that. I will tell you a couple of other examples. I wasn't necessarily in such a strong lead position, but other things. I don't know if any of you have relatives who need hearing assistance, but if you do, maybe you know that if you go to the conventional way of getting hearing aids, it costs thousands of dollars to get the assistance that you need. We wrote a report for President Obama because he asked us what could be done. And what we found out is that the kind of technologies that people who are bird watchers, the listening technology, you can actually use that to improve people's hearing, and it doesn't cost thousands of dollars. We called for changes of regulations for the FCC to make this possible. And now anyone, like I said, if you have relatives who are having trouble with their audio perception. This conventional way is you go to these people called audiologists, and we wind up spending something like $5,000 to get aid. You can walk into these places where these electronic bird watching technology exists, and you can get a better quality product for $500. That's something we did during that presidential advisory group. And then the final one is that most of you walk around with smart devices on your person, and you use them to communicate with people. In one of our meetings with the president, he brought some data to our group, which was that within 5 years, if we continued to use electromagnetic Wi-Fi in the way that had been the tradition, there would not be enough for every American to have a smart device. And he asked us to fix that problem, and we did. And that's why a lot of you still have access to Wi-Fi.
Let's do one more, and then we're going to wrap it up. Dr. Gates has to get up really early in the morning to go to Charlotte to get back to teach. So we're not close to anything, as y'all know. So it's going to take a while to get there. So let's go one more. Is there one last question?
Well, I already asked one, but if somebody else would like to ask one, then I can. But I did have one.
Anybody else? Not that this question will be great, but now I'm building it up, so here you go. Right.
Hello. Another nerd question, I guess. Is there anything about current public policy that you think should be changed that would make it better for young people to go into STEM and for people to stay in STEM?
Yes, loan forgiveness for college. I gave my answer.
You gave your answer, right?
Loan forgiveness for college.
Right. Pretty good. Thank y'all for coming. Thank you very much for traveling. I know it was not easy getting here. I really appreciate it. Thank you so much. Thanks, y'all.